a very nice, reasonably priced textbook on lambda calculus and combinators was written by two students of Church, Roger Hindley and John Selden, and it's very cleanly written, very nice, has lots of bibliography and other things in it, and lots of worked examples. And so you can easily get it from Amazon.com by tomorrow, I'm sure. And so I recommend that as a textbook kind of introduction to it. The title is Lambda Calculus, spelled out with two words, and Combinators, and Introduction. And I think it's in the bibliography that I put in the background materials as well there. Okay, I see I'm not actually going to, oh yes, I'm going to do a little bit of it here. Yes, okay, I will do it, okay. So, this is just a quick example of primitive recursion, and when you do primitive recursion, of course you can have any number of variables, and you only do recursion on one of them. Primitive recursion is a one-step kind of recursion, and so what you do is you take all the projection functions. A projection function takes a sequence of variables and projects onto the 17th, for example. It's the generalization of identity function. So you take the constant functions, the projection functions, of course you need the successor function, and when you make things there, you use composition, ordinary composition of functions. I'm not talking in the language of combinators here like this. I'm talking in mathematics here. Everybody knows what a composition of functions is. And so you form new functions from those given functions by composition and simple recursion. For example, if f and g are given, and you want a function of two variables h, by recursion, you say, oh, h at 0 was just that f, whereas h at n plus 1 calls up n, calls up x, and calls up the previous value of h. That's the step from n to n plus 1. I'm doing it, and so that's called this scheme of simple recursion there. And so, as I was saying, Gödel was able to show, I mean, people had studied them very much before that, but he was able to put them right to work to do all the coding up of syntax using primitive recursive functions. And of course, eventually, we wanted to think of what is recursively enumerable here. And recursively enumerable really means I start doing something over and over again and getting lots of good answers out of that. And then if I have a systematic way of doing it, then the combination of all of the, I don't mean combinator combination, the set of all of those things has been enumerated by setting up how you got all the things there. So a very simple example of enumeration is to take a primitive recursive function and apply it to any integer argument there. And now here's important trick there. If P is, say, some kind of syntactical analysis, and N is some data that you put in for the input there, it may be that the data was inadequate to get a good answer. So what I'm going to say is that my syntactical analysis, if N was not sufficient amount of information there, I'm going to say the answer is 0, meaning you lose. But now, when I do my syntactical analysis here, if I give it enough information there, and I say, whoa, you found it, then I give the answer as what was found plus 1 is positive there. 0 means you haven't gotten there yet. M plus 1 means you did get there, and what did you get? you got M there. And so with this definition of primitive recursive functions there, you can write down a definition of any recursively enumerable functions. I'm not giving a course in recursive function theory here today, but just to point out that the relation between primitive recursion and recursively enumerable, which Kleene developed, is a very simple-minded thing there. And the key thing is that primitive recursive functions tell you how to follow rules in manipulating finite expressions, which can be represented by Gödel numbers. That's the
add a little bit more to that?
Oh, please. I think another good example of it to fit in there is you could take an equation between two primitive recursive functions, p of n and lots of other variables equals q of n and lots of other variables. And so if you put in particular numbers for the variables, of course, you can check it's either true or false, it's decidable. But if you ask the question, does there exist an n such that p of n and blah, blah, blah equals q of n and blah, 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 that's a harder thing there because you have to keep searching to find out if there were an n that did it. Well, that form of existential generalization on a decidable predicate is another example of recursively enumerable. And you can use primitive recursive functions and set up there to show the equivalence of all of those things. By the way, a partial recursive function is just a partial function whose graph is recursively enumerable. That's another way of connecting up. Kleene discovered that you have to go beyond total functions that were a favorite in the primitive recursive functions. And so he introduced partial functions, and it was really a good idea. Gödel didn't have that idea, and it makes much more sense also in understanding Turing machines and other things there to think in terms of a function that is sometimes defined and but is only partially sometimes undefined, but is still computable. You start out computations, and if you're lucky, it's defined and you get to the answer. And if you're unlucky, it may go on forever searching for something that it can't find there. And of course, the partial recursive functions have recursively enumerable graphs, but also either the domain of a partial recursive function is recursively enumerable, the set of n's for which the partial function is well defined, that's an example of recursively enumerable, or the range of the partial recursive function is another example of recursively enumerable set. So there are lots of different equivalent definitions of recursively enumerable, but I like this for being so direct there in terms of primitive recursion. But of course you have to get those other equivalences as well. Okay, so oh good, it's only half past here. I've done this now. Before, I was speaking mathematics. That's the kind of definition that you're just given in a mathematics book to say what it means to define by recursion. H is defined by primitive recursion from F and G, okay? But now let's use our formalism there and rewrite the things in terms of application there. And we want to take advantage of Church's numerals. So this is what Church didn't know how to do, was to show that all the primitive recursive functions could be defined in the lambda calculus. So all I've done is rewritten the mathematics there in terms of applicative things there, and I've used the Church numerals in there instead of the integers. When I was talking in mathematics, I could talk about integers. But now when I'm talking in Church, I'm talking in terms of his numerals, his iterators that do it. So that's the same problem of trying to find H given F and G there, so that when you use the numerals there and work out the combinators, you get the right equations for it there. So I've written it down there, but forgive me, I don't have the strength to go through all the steps of making it out. In fact, these kind of expressions are expressions that only a machine could love, really, there. So you see, again, we want to set up a stepwise thing of going from n to n plus 1, and then h itself could be computed by doing that step n times and then taking out of the answer, you got just the amount of data you needed in order to get the answer. It's very similar to the trivial definition of predecessor, but here we have to keep track of more data as we're doing this computations of passing from n to n plus 1 in it. And of course, you could do more recursions and things like that. And so I have to leave those as exercises. A different way of doing combinators, instead of setting up all of that data, remembering all of that data, you can just think in terms of getting replication, self-replication, doing recursion by self-replication. So the Y combinator is that combinator that says, can I replicate things by using just lambda-calculus rules? And so the whole thing comes out in terms of self-application. So I guess we can see if we can illustrate it here. And they didn't understand it at first. Turing actually, when he came to do his thesis work under Church, found a version of it. Curry hadn't done it before. Kleene did it by that data structure method that I was talking about, by stepping things through and recording all the results that you need and all the steps there. But you can get much quicker definitions if you use self-application, and this became very popular then there. So mathematician would say this is a completely nutty thing to write down there, because there is no mathematical object that can apply to itself. You know, real numbers are real numbers. Continuous functions of real numbers are different. Of course, you can compose two real functions, but you don't apply a real function to itself because it's a type mistake. A continuous function is not a real number. It's another type. And so mathematicians wouldn't do this kind of thing. But what happens in the lambda calculus is if you take this expression and apply it to itself, then you see you have two copies there, two copies of the same thing. Now, if we take the rules of the lambda, we have to insert that in for the variable x. And so the answer will be f of, insert all that crap in for the variable x, okay? Okay, just a minute, I'll do it. Have to do it once more. And what did I get? Well, I got the f out front here, and then inside I got this crazy thing replicated. And so that self-replication can be achieved by self-application, and you stop to think. So that means in the lambda calculus, or in the combinators here, no matter what f I think of, I can find some sort of crazy thing. I'm running out of letters here. Okay. I'm running out of letters. I have to think of another word. Okay. Absurd. Okay. You can find some absurd thing which, when you work out what it's doing, is whatever that absurd thing was, when you calculated out what it was, it put the f in front and replicated the absurd thing over again. Now, I'm sure you know from programming that recursion can be done by fixed point equations. And of course, there are many types on which you can do things like that too. But this is a fast and dirty way of doing recursion by replicating things. And you can take examples there. So I've given some examples of the factorial. Factorial is the most overdefined function in the history of mathematics there. The factorial of the function is the fixed point among functions which either says when n is 0 you take 1, or if it's positive then you multiply n by the previous value. So the fixed point operator there immediately gives a definition of what the factorials do, and we use that kind of programming all the time there. But of course, if you wanted to implement all of that, you'd probably go back to Claney's style of keeping track of what all the stages of the computation were. But this certainly makes it much faster there. And so, of course, it also shows that because all the recursive functions can now be obtained in the ways shown there, trying to decide equations between two combinators, we have very simple axioms for the combinators, right? It's a very simple algebra here. A very simple algebra there. There's no way to decide whether two things are equal on the basis of these axioms. This is an example of Gödel's incompleteness theorem there. There is no decision method here for deciding equations between combinators, as you could prove on the basis of these axioms. Why? Because we can put the whole recursive function theory into combinator notation. I think I want to finish up here for it. So yes, let's finish a little bit early. We'll get in ahead of the line in the lunchroom there. Now, instead of combinators, the combinators are all very good, and very often combinators are kinds of programs that are useful in making new programs out of old programs, and combinators can be very helpful in setting up things there. But really the important thing is the way a value depends on the variable there. So now we can make lambda, if we like, into an operator that says it forms the function of x about whatever we then write down there, what kind of value we want to get out of x. Let's think of the function of x that gets values depending on x in that way there. And so now, instead of Curry's combinators, and I say they can be very nice, the INRIA people, for example, implemented languages by using the combinatorial abstract machine there. The combinators And as I say, only machines can love them, but the combinators can be used as a very succinct notation for writing compilers. And so there are people who use combinators there. But if you're trying to explain why things happen, combinators sort of divide things into very minute steps. And so sometimes it's better to say, I want to think of the whole damn function there. And so let's have a notation for the function itself. So that's what lambda does. And the key axiom there is the second equation that says, if you define a function taking on values according to the expression m there, then if you apply that function to the argument, what you have to do is to substitute in the argument for the variable and carry on. Now we come.
Divided by x is substituting.
Yeah, it's just a shorthand for substitute y for x in m, substitute n for x in m. Okay? Now, what's the problem? It looks very nice, but what's the problem with this? Capture of free variables by the bound variables. The lambda operator is a variable binding operator. Lambda x of m has no x in it anymore, so to speak. It's a function of one argument, but it doesn't have the symbol x in it anymore in a certain sense. When we thought of it as syntactical transformations, x was eliminated there. Now, when you make a substitution of n for x and m can have other variable binding operators in it, and you don't want to confuse the use of those. Jeremy, I think you're a good person to think of an example here of how you have to watch out about the clash between free and bound variables. Can you do one off the top of your head? Oh, come on.
I know I had one written down earlier.
Oh, okay. Let's do one here. Okay. No, you just have to say there's going to be a problem here.
I have to say, and I can program languages where they point out little things you go wrong. Yeah, sure. So we have substituting x to y in lambda x of x. Right. Yeah, that's very short. And then we get this one.
Well, wait here. You see, the thing is, what x is going to evaluate here could be a function abstraction in itself. And so that would be function of two variables there. That would be an example where when you have the scope of x, you have another variable binding in there. And now, if you want to apply this to, I can apply it to anything. Why don't I apply it to y? I always liked y. Was a good chap. Okay? Now I have to be awfully careful, because if I do it blindly by substituting in for x, I'll get lambda y f of y of y. And that answer is wrong. What this should be is something completely different from what you're binding here. This should be something else. And what you want to do is put that something else in there and leave the y working on that. And so that's the problem, that these are only placeholders. I could have used an entirely different letter. And then if I applied to y here, with a different letter it should be the same. And then if I did y, it's okay to have y in y and lambda a like that. So compilers spend an awful lot of time keeping you from doing those mistakes. There's a notation of de Bruijn indices which can be implemented very, very nicely in formal languages. But as far as I'm concerned, it's the devil-owned trouble to write it down so that you never have a clash between free and bound variables. But if you're just careful, you'll be okay unless some nitpicker comes and challenges you. Do you have some other example, Jeremy, you'd want to say?
Just lambda x.z, and then you substitute z for x.
Yeah.
This is the other one.
Yeah. Right. You don't want to do this substitution. I'll write it in this other notation. Lambda x dot z. Okay. There's a variable there. Okay. And now we say, oh, okay. Why don't you substitute in x for z? And you say, all right, I'll do it. Give me time here. Lambda x. Wrong. Right? Because what it should be is lambda new variable. You should rewrite the bound variable so it won't clash with this one. You should rewrite this as some other variable. It doesn't matter what variable you use as long as you're consistent about them.
You can use that alpha renaming, that first equation there, to move it to some new variable that doesn't clash.
So,
Maybe one more comment about the drawing, because this connects
Oh,
to
yeah,
the
yeah,
question
please.
that you had earlier about categorical semantics. And oftentimes, those categorical semantics use the De Bruyne indices instead. So that's an alternative sort of way of getting rid of the variables and avoiding these troubles.
you see, when we do things by pencil and paper, we use the eraser an awful lot. And for machine kind of thing there, it's better if you make up an algorithm that checks the scoping ahead of time, and then once you know the scoping, you won't make any mistakes. But we just usually do it by eye, and then, as I say, erase the things where we did it wrong.
And maybe one more comment about the examples that we've seen. They all had free variables to begin with. And you might be wondering, well, programs don't, my type checkers don't allow me to have any free variables, so does this problem just go away? And the answer is no, it doesn't. We could have made a bigger program with a binder further out, and then if we were trying to do beta reduction inside the program somewhere underneath the binder, then that's where we still have problems with these variable captures, and we still have to be careful about how we do our substitutions.
Okay, so
The question is an outsider to
where are you?
if you have all those binding problems, you also have the scoping problems, that you have this confusion now that arise from that. Why in the first place would people just use the same symbols for free variables or variables that are
Because those other notations, whether combinators or De Bruyne instances, are very hard to read.
I think he's asking the question, why not just always use different variables everywhere?
exactly, like for example,
Oh yeah, that's, yeah, I mean, people who in doing systems of predicate calculus say free variables are from one alphabet and bound variables are from entirely different alphabet. And then, of course, you have to know how to make substitutions, but if you say that all bound variables are from a completely alien alphabet, then you wouldn't have that clash. So that's a possibility too.
There's also sort of a second part answer to that, which is that because of duplication, and we just saw that with the Y Combinator, even if you start out with a program where all the variables are distinct, as you start running the program and you're duplicating things, you will end up with the same variable appearing in multiple places. And so then at runtime, you still, if you were thinking in terms of the lambda-calculus, you'd still have to be careful with your substitution. And so it's not a panacea.
Yeah, what the computers have to do and what the humans should do is to be precise about what the algorithm for substitution really is. And then you're okay. Most of the time we just say, oh, I can see how to do it, so don't bother me. Please.
It might be worth mentioning that there are also explicit substitution calculi
Yes, yeah, sure. Yeah, it's been a big bone of contention. So Carnap was a famous logician. I think certainly maybe Church commented on it. Carnap wanted to formalize higher order logic, and there's a big question of how you substitute a higher order formula in for a higher type variable. And the original formulations were completely wrong there, and that's an example of where there are lots of pitfalls if you don't keep the clashes clear. Yes.
I was wondering if you could tell me how to pronounce the word Barengret?
Oh, okay. Yes. Hank Barendrecht. You have to be careful because if you put in one other letter, it's an obscene word. So Drecht doesn't have an extra H in it. Barendrecht, and his name is mentioned many, many times in the bibliographies that we have in the background material. He wrote a big book on lambda calculus. He started with his thesis, and then by the time he wrote a giant book there. But I think Hindley and Selden there say all the basic things there in much shorter thing. But Barendrecht was very interested in many, many different kinds of problems and other ways of using lambda calculus, and so it's a pretty hefty text, but he's an outstanding researcher. Okay, let's break for lunch. Thank you.